will continue answering the questions about Chapter 8, Section 1, which is about the quantization of energy, Blackbody radiation, photoelectric effect, and Compton shift. Question number 1. The emission of electrons from a metal surface that occurs when the light of certain frequencies shine on the surface of the material, called a photoelectric effect. Question number 2. According to Einstein's photon theory of light, what does the intensity of the light shining on a metal determine? According to Einstein's photon theory, light is composed of photons, and each photon carries energy which is equal to h times f, and intensity of the light is determined by number of photons. So if number of photon increases, intensity of the light increases. A. The number of photons hitting the metal in the given time interval. Yeah, this is the correct answer. B. Energy of the photons hitting the metal. Energy of the photon is not yet about intensity, it's about energy of a single photon, which is represented by h times f. But intensity of the light can be determined by number of photons, so you should multiply hf by how many photons are striking the surface or hitting the metal surface. So maybe you can say that it's n times hf is the intensity, determined intensity of the light by number of photons multiplied by energy of a single photon. C. Whether or not a photoelectrons will be emitted. So this is not about intensity, it's about the energy of a single photon. When energy of the photon is enough to overcome the work function, so then photoelectrons will be emitted, we know that. Kinetic energy of the emitted photoelectrons. Kinetic energy of the emitted photoelectrons also depends on the energy of the photon. Remember Einstein's photoelectric equation. Kinetic energy maximum is equal to energy of the photon, which is hf, minus work function of the metal, which is hfo. So if you want to increase the kinetic energy, you have to increase the energy of the photon, because metal, work function of a certain metal, is constant. Question number 3. At the peak of the sun's radiation spectrum, each photon carries energy about 3.2 times 10 to the power negative 19 joule. What is the frequency of this light? F is the question in here. Energy is given. So energy is equal to h times f, you know that, for a photon. So if you want to calculate f, we have to divide energy by Planck's constant h. So f is equal to energy 3.2 times 10 to the power of negative 19 divided by h is 6.63 times 10 to the power of negative 34. Now let's apply the calculator. 3.2 times 10 to the power of negative 19 divided by bracket 6.63 times 10 to the power of negative 34, close the bracket. Answer is 4.8 times 10 to the power of 14. So this is the frequency of this photon. Question number 4. What is another word for quantum of light? Quantum of light is the expression which is used by Max Planck. So Einstein named this as photon. Question number 5. Which of the following metal will exhibit the photoelectric effect when light of 7 times 10 to the power of 14 Hz frequencies shine on it? We know that if energy of the photon is greater than the work function, so in this case, or equal than the work function, we will observe photoelectric effect. So we should first calculate how much energy of this frequency of the photon is, and after that we will compare this result by these given numbers. So let's calculate energy of the photon first, which is h times f. So h is 6.63 times 10 to the power of negative 34 multiplied by f 7 times 10 to the power of 14. So let's get the answer. 6.63 times 10 to the power of negative 34 times 7 times 10 to the power of 14. Result is energy of the photon is 4.64 times 10 to the power of negative 19 joule. But when you check the choices, energy is not given in terms of joule. You will see it's given in terms of electron volt. So that's why you have to first convert this joule into electron volt. How much is the energy of the photon? We can convert joule to electron volt by dividing 1.6 times 10 to the power of negative 19. So this is the energy in joule for a single photon divided by 1.6 times 10 to the power of negative 19. So I will get the result divided by bracket 1.6 times 10 to the power of negative 19, close the bracket. Answer is 2.9. So energy of the photon is 2.9 electron volt. If work function is less than that number or equal to that number, we can observe photoelectric effect. So 2.3 is less than 2.9, so you can observe photoelectric effect. 4.7 is greater than 2.7, not observed photoelectric effect. 2.14 is less than 2.9, you can observe photoelectric effect. Yani A and C, you can observe photoelectric effect, but B cannot be observed, so this is the correct choice. Both A and C are true. And question number 6. A photon in a laboratory experiment has an energy of 5 electron volt. What is the frequency of this photon? Energy of the photon, equation for energy of the photon must be used, but first we have to convert energy of the photon from electron volt to joule. To do that, we have to multiply electron volt by 1.6 times 10 to the power of negative 19. So 5 times 1.6, 1.6 times 5, which is equal to 8. So result is 8 times 10 to the power of negative 19 joule. This is the energy of a photon. We can calculate frequency of the photon by dividing energy of the photon in joule divided by Planck's constant. So 8 times 10 to the power of negative 19 divided by h is 6.63 times 10 to the power of negative 34. So we can get the result 8 times 10 to the power of negative 19 divided by 6.63 times 10 to the power of negative 34, close the bracket. Answer is 1.2 times 10 to the power of 15. 1.2 times 10 to the power of 15 hertz is the answer. D is the correct choice. Question number 7. To measure the Compton shift, which of the following waves are used? Compton shift can be observed by very high energy photons. Those photons are X-ray photons. So B, you should use X-ray photons to observe Compton shift. Question number 8. When the photoelectric effect happens, if the intensity of the light ray increases. So according to photoelectric effect experiment, intensity of the light determines number of photons. So number of photons increases. If photoelectric effect happens, of course, each photon removes one electron, number of photoelectrons must increase. So A, the number of emitted electrons will increase. Correct. This is the correct answer. So why? Increasing intensity means greater number of photons in the light. Each photon goes to one electron. If the greater number of photons goes to greater electrons, greater number of photoelectrons will be ejected. So number of emitted electrons will increase. Correct. Number of emitted electrons will decrease. Not correct. Kinetic energy of the electron will increase. Kinetic energy of each electron depends on energy of the photon, not intensity. So this is not correct. Kinetic energy also will decrease, not correct as well. So A is the correct answer in here. Question number 9. The graph shows a linear relationship between the maximum kinetic energy of the emitted electrons and the frequency of the incoming light in the photoelectric effect. What is the straight line slope represents? Remember, we said that H is delta change in kinetic energy maximum divided by delta F. So when we divide this kinetic energy, change in the maximum kinetic energy divided by change in the frequency, we calculate the Planck's constant. So slope represents Planck's constant. Question number 10. If the energy carried by one photon of violet light is 4.42 times 10 to the power negative 19 joule, what is the wavelength? So we will use the photons equation, but this time we will use the equation in terms of not frequency, in terms of wavelength. We know that energy of photon h times f, and we know that frequency is equal to speed divided by wavelength. So we will write instead of f, hc divided by lambda. Because lambda is the question, I have to cross product, and the equation is going to be lambda hc over energy of a single photon. Let's calculate the wavelength now. H is 6.63 times 10 to the power of negative 34 multiplied by speed of light is given in the question 3 times 10 to the power of 8 divided by energy of single photon 4.42 times 10 to the power of negative 19. Now let's calculate, we will calculate the result in meters. 6.63 times 10 to the power of negative 34 times 3 times 10 to the power of 8 divided by bracket 4.42 times 10 to the power of negative 19, close the bracket. Answer is 4.5 times 10 to the power of 7 power of negative 7 meters. This is meter, but choices are given in nanometer. I have to convert meter to nanometer by multiplying 10 to the power of 9. So if I multiply this by 10 to the power of 9, result is going to be 450 nanometers, which is A is the choice. Question number 11, which of the following shows the photons have linear momentum? So Compton shift, Compton effect. When a photon hits an electron, remember the experiment, it makes the electron, free electron, to recoil. So of course, if it is recoiling, photon must be transferring some of its momentum to the electron. So which shows you that initially photon has some linear momentum. Question number 12. This figure represents the experiment. Which experiment? Compton shift, because there's a stationary free electron. When stationary free electron is collided by a photon, so it recoils, photon scatters. So this experiment is called Compton experiment or Compton shift. Question number 13. If the frequency of electromagnetic ray is 3.2 times 10 to the power of 11 Hertz, what is the energy of this ray? It's very easy, just you will multiply. Energy of photon is equal to h times f H is 6.63 times 10 to the power of negative 34 multiplied by frequency 3.2 times 10 to the power of 11. So let's do it. 6.63 times 10 to the power of negative 34 times 3.2 times 10 to the power of 11. Answer is 2.12 times 10 to the power of negative 22 joule. So this is the correct answer. Question number 14. At the photoelectric effect, it's found that when a photon of 8 times 10 to the power of negative 19 joule incident on a metal surface, electrons ejected with a maximum kinetic energy 4.8 times 10 to the power of negative 19 joule. Find the work function of the material. So we know that kinetic energy of the photoelectron is calculated by HF multiplied by HFO. So HFO is the work function. So I'm going to calculate work function. So that's why I have to take HFO, it is negative on the left side as positive. So kinetic energy maximum on the left is positive. We should take it to negative as negative, to the right as negative. HF minus kinetic energy maximum. So the work function, HF energy of the photon is calculated and given directly, so we don't need to calculate it, just write the number 8 times 10 to the power of negative 19 minus kinetic energy of the photoelectrons 4.8 times 10 to the power of negative 19. So result is going to be 3.2 times 10 to the power of negative 19 joule. This is a work function in joule. But the answers are given in electron volt. I have to convert joule to electron volt. Work function in electron volt is going to be work function in joule divided by, of course, 1.6 times 10 to the power of negative 19. So 3.2 times 10 to the power of negative 19 divided by 1.6 times 10 to the power of negative 19. So the result is going to be 2 electron volts. So this is the correct answer. Question number 15. One of the following materials does not exhibit photoelectric effect when light of 14.14 shines on it. We know that if the energy of the photon is less than a work function, there will be no photoelectric, or vice, or we can say like this: if the work function is greater than the energy of the photon, in this case you cannot observe photoelectric effect. So A, work function is 2.25. It is less than 4.14. So that's why photoelectric effect is observed. This is positive, so this cannot be the answer. 2.36 is less than 4.14, so we can observe photoelectric effect. It's not the answer because it says not. 3.9 is less than 14.14 electron volt. So again, you can observe photoelectric effect because work function is less than energy of the photon. But 4.5 electron volt is greater than 4.14 electron volt. As you see, work function is greater than energy of the photon. So in this case, you cannot observe a photoelectric effect. So this is the correct answer. One of these scientists was able to resolve the conflict known as ultraviolet catastrophe. So Max Planck solved this conflict. Question number 7. Which of these 4 photons have more energy? Energy of the photon is calculated by, we know, H times F. Of course, the one which is a greater frequency will have a greater energy, or if you write this equation in terms of wavelength, the one which has a longer, shorter wavelength will have a greater frequency, greater energy, or greater frequency, greater energy. So shortest wavelength in here is violet. So we know that from violet to red. So what wavelength decreases? Increases, but frequency decreases. So that's why violet has highest frequency, shortest wavelength, greatest energy compared to red. Question number 18. An X-ray photon is scattered by a stationary electron. This is talking about the Compton shift. How does the frequency of the scattered photon change compared to its frequency before being scattered? We know that photon transfers some of its energy to these electrons stationary, which is initially. So if the energy of the photon is transferred to the electron, of course energy of the photon must increase. So if the energy of the photon increases, we know energy of the photon is represented by h times f. If energy of the photon decreases, when some of the energy is given to the electron, so frequency also must decrease. The scattered photon has no frequency, not correct. Of course, there must be photon. If it says photon, it's a frequency. Frequency stays the same, no. Frequency higher, no. It becomes lower. So correct answer is D. Question number 19. A specified mass falls from a specific height. If all of the energy of this mass, which is 14.7 joule, could be converted to the visible light of the frequency 6 times 10 to the power of 14 Hertz, how many photons would be produced approximately? So this energy total, all this energy will be converted to photon. How many photons we will calculate? But first we should calculate energy of a single photon. So there is required information in here. Let's calculate energy of a single photon, which is h times f. But we know that energy, if the single photon has one hf energy, if there are 2 photons, total energy is going to be 2 hf. If there are 3 photons, total energy is going to be 3 hf. If there are n photons, total energy is going to be n times hf. N times hf. So if we want to calculate n, so we have to simplify hf on the right. So by dividing both sides by hf, so this is the equation how we calculate number of photons in a energy when a total energy is given. So n is equal to total energy given divided by energy of a single photon. So let's calculate it. N is equal to total energy is given 14.7 joule. Yeah, it's joule. Energy of the photon must be calculated in joule if the total energy is given in joule. So I can calculate it. H times F. H is 6.63 times 10 to the power of negative 34 multiplied by frequency of the photon 6 times 10 to the power of 14. So denominator is joule, numerator is joule. So then we can divide it 14.7 divided by, in bracket, 6.63 times 10 to the power of negative 34 times 6 times 10 to the power of 14, close the bracket. Answer is number of photons 3.769, almost 7 times 10 to the power of 19 photons. So this light consists of 3.7 times 10 to the power of 19 photons, which is B is the correct answer. Question number 20. What is the relationship a joule and an electron? Well, it's very easy because we know 1 electron volt is equal to 1.6 times 10 to the power of 19, negative 19 joules, so A is the correct answer. Which of these phenomena provides support for Einstein's photon theory of the light? Of course, the experiment done after Einstein's photoelectric effect is the Compton shift. Compton shift. Question number 22, sorry. According to the classical physics, so this question is about classical physics, and before the experiment, what is being taught? When a light illuminates a photosensitive surface, what should determine how long it takes before electrons are ejected from the surface? Of course, before the photoelectric effect, it was believed that as the number of photons illuminating the surface increases, so they thought that electrons can be ejected. So, but after some time, and the number of photons determines the intensity. So that's why before the photoelectric effect experiment, all scientists believed that, classical physics said that intensity, very intense light can remove electrons from the surface. But after the experiment, it's observed that it's not correct. So after the experiment, we saw that, or they saw that energy of a single photon is important, not brightness of the light, not intensity of the light for photoelectron emission. Question number 23. The failed prediction of classical physics that energy is radiated by a black body at an extremely short wavelength is extremely large, and that the total energy is infinite, is ultraviolet catastrophe. This is the definition of ultraviolet catastrophe. Question number 24. Blah 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 is the lowest amount of electromagnetic energy that exists in the universe and has zero mass. It is the definition of photon. Question number 25. The Compton shift delta lambda can be observed using, so we need to use high energy photons. X-rays are high energy photons in here. Question number 26. Light of energy 4.14 electron volt, which is the energy of the photon, shines on lithium, which has a work function 2.3. What is the maximum kinetic energy of the photoelectrons? Very easy question. Kinetic energy, maximum kinetic energy of the photoelectrons is calculated by energy of photon minus work function of the metal. So energy of the photon is HF is given as 4.14 minus HFO, which is the work function, is given as 2.3 electron volts. So both are electron volts, so no need to conversion. 4.14 minus 2.3, which is 1.84. 1.84 electron volt is the maximum kinetic energy of the removed photoelectrons. Question number 27. Which of these photons has the shortest wavelength? Shortest wavelength, the one which has the greatest energy and also highest frequency, yani violet. Violet is the photon in here which has the shortest wavelength, greatest energy. Question number 28. According to the classical prediction of the photoelectric effect, classical prediction means before the experiment, the kinetic energy of the ejected electrons from the surface of metal depends on, before the experiment, both electron ejection and kinetic energy of the photoelectrons all are thought to depend on the intensity. And intensity of the incoming light is the correct answer. But after the experiment, it's observed that no, it is not depend on intensity. It depends on the frequency of a single photon or energy of a single photon. Of course, frequency of a single wavelength, single photon's wavelength, or energy of the wavelength. So echo before the experiment. Answer is B. After the experiment, this answer changes to A and C. This question can be written in another form. According to the experimental data, if the question was like this, answer would be D. But before the experiment, it was believed that intensity of the incoming light determines if what electrons will be ejected and how much is the kinetic energy of ejected electrons. Equation 29. The equation HF is called Planck's equation for a photon. Planck's equation. The constant h in the equation is equal to, what is unit of the h? It's very easy. H is equal to E divided by F is Joule. F is the frequency, which is hertz or 1/2. When you flip this 1/2, it becomes Joule times second. Joule times second Or you can say that Joule divided by Hertz, also possible. So Joule divided by Hertz also can be answered for this question. Question number 21. 4 lights each has 1 joule of energy and their wavelengths are 650, 600, 500 nanometer and 450 nanometer. The number of photons of which light is the smallest? Remember, we said that energy, total energy is equal to energy of a single photon multiplied by number of photons, because one photon if has 1 hf, 2 photon 2 hf, 3 photon 3 hf, 4 photon, and photon has n times hf total energy. So because we will compare the energy in terms of the wavelength, I have to write an equation in terms of wavelength. Total energy is going to be n times hc divided by lambda. So if I will calculate n, I have to take this hc over lambda to the left side. So, but we should flip it. Yani total energy multiplied by wavelength divided by hc. hc will represent the number of photons. We want the number of photons to be smallest. If you want number of photons to be smallest and smallest, wavelength of the light must be smallest as well, according to this equation. So smallest wavelength, which one? 450 nanometer. So for 450 nanometer light has this smallest number of photons. If you want to get all these photons to have 1 joule of energy. Question number 32. If the wavelength of a photon of violet light is 450 nanometer, what is the energy carried by the photon? So just again we will use the same equation, energy of the photon equation in terms of wavelength, hc divided by lambda. So h is 6.63 times 10 to the power of negative 34 times c 3 times 10 to the power of 8 divided by wavelength. Wavelength is given in nanometer, but because others are in terms of SI unit, we should convert 450 to meter as well by multiplying 10 to the power negative 9, because nanometer is converted to meter by 10 multiplying 10 to the power negative 9. 6.63 times 10 to the power of negative 34 times 3 times 10 to the power of 8 divided by 450 times 10 to the power of negative 9. Close the bracket. Answer is 4.42 times 10 to the power of negative 19 joule. So answer is A. Question number 33. The threshold frequency FO of a metal, both work function and threshold frequency depends on only the type of this metal or solid. Type of the solid depends on number of photons. No, where is the type? Differs from metal to metal. Yes, for each metal this is different. No other factors determine the work function. No other factors determines the threshold frequency. Only the type of the solid. Question number 34. Which of the following scientists could explain the photoelectric effect successfully? Of course, photoelectric effect experiment is done by Albert Einstein. So these are all about the photoelectric effect mystery questions.